Okay, so we just got done talking about all the different um, properties of a wave. There's a few that we should still hit. So at this point, before you go any further, just double check your diagram and make sure that what you've labeled on there is really what we've described so far. Or if any questions at this point, what do you think they are? Because we're just about to move into what it should look like. So just so you're an idea, you don't have to mark this over and over again. Just know that let's start with crests. Crests are the highest points on a wave, and troughs, kind of like a feeding trough, are the lowest points of a wave. The distance from a crest to what we call the rest position or rest point, which will be this line here, that's sometimes called the nodal line, is the amplitude. That can be from the crest to the rest point or the trough to the rest point, either one. You don't have to have this on your diagram, but it's important to remember this. It's an up and down motion that creates the motion in a direction. So say somebody, you pulled your rope up and then down, it would push the vibration or the wave out this way. The wavelength can be measured from crest to crest, from what we call the node line or node point here and node here, or from the trough to trough. It doesn't make a difference as long as it's from where the wave starts to where the wave starts again. That's the full length of the wave. All right, and just basically how fast this is going is the wave speed, not how fast up and down, but how fast in a direction, right or left, would be the wave speed here, or the wave velocity. And the frequency is how often it goes up and down. So it's actually a measurement of how much time it takes to go through one full cycle. So if it goes from crest to crest in 1 second, it will be 1 cycle per second. And once again, the units we use for that are hertz. Okay. So moving on to a different thing here. We're thinking about like, why is it so important to know about amplitude, wavelength, wave speed? And I want you to take a look at these two pictures here for a moment and just really think, what kind of waves could have caused these disasters? Maybe at this point you have the kind of a vocabulary to be able to describe the kinds of waves that would have had to be there. For instance, this might be high amplitude, right? Would it have been a fast wave? Would it have had a long or short wavelength, do you think? Do you even know what kind of wave specifically would have caused something like this? Okay, hopefully you've taken some time to really think about it. Just to give you an explanation here, the picture on the left is a picture of a major earthquake, or not a picture of an earthquake, but a picture of the results of an earthquake. And on the right here is really the results of an earthquake as well, but an earthquake that caused the tsunami, which are caused by earthquakes when the earthquakes are out in the ocean next to a landmass. This one was in Indonesia, where like over 250,000 people perished. It was terrible. Back in 2010, I believe, maybe 2004. And this earthquake over here, it was, I think this one may have been in Haiti from 2014, which is also another devastating earthquake. So we're going to talk about these things right now. There's not really a better time to do it. Seismic waves. Seismic meaning in the earth, I believe. Actually, I'm going to check that real quick. So it's actually to shake is what seismology means. So a seismic wave is basically a shake wave, which doesn't really make sense to me because all waves shake. So whatever. Interesting fact of the day. The question here is, what are earthquakes and how do they act in waves? What kind of waves are they? If you were to classify earthquake waves, just take a second to think about this. You stop and jot about it. How would you describe and classify an earthquake? You think, would it be, in terms of its form, would it be longitudinal or transverse? And in terms of its need for a medium, does it need something to go through? And the answers to these questions are yes, it needs something to go through. That's why it's called an earthquake. The only thing that doesn't need something to go through is light. So it's a mechanical wave. And also, it's kind of curious, it could be a longitudinal or a transverse wave. There are multiple types of waves that create or that are present in earthquakes, both pushes and pulls and up and down motions as well. So seismic waves. These are the waves that move through the ground during an earthquake. You may remember this from last year. You have the focus of an earthquake. Sometimes these are subduction zones, where you have continental plates moving against each other or minor plates moving against each other. A lot of times the foci or the focus of this earthquake is far into the ground. The epicenter is the point right above the focus on the ground itself, but the waves radiate out from these many places where you have vibrations. Anytime you have, like, say, a plate touching against a plate, you might have a snapping, boom, and then the vibration comes out from that, just like you can hear your knuckles moving against each other. Literally, the sound from that vibration is the same thing that happens in the earth, except kind of a lot bigger. A little bit more amplitude there, for sure. So these waves will travel out from that focus, and then when they hit the surface, that's when we start to actually feel them. Now, there are a couple different types of earthquake waves, as they call them. You have primary waves, which are longitudinal waves. Primary meaning that they travel fastest. They'll get there first. That's what primary means. And then secondary, which are transverse, meaning it's from up and down shaking. So you have back and forth shaking and up and down at the same time. The secondary will travel slower, but you also a lot of times have aftershocks. You'll have reflections of these waves hitting and then bouncing off of each other and then eventually coming back again. So you can actually have a mix, and that's not a good thing. It's not like you want a little bit of this and a little bit of that when it comes to earthquakes. They can be quite problematic when you have that. You can also have it in multiple directions at once, which gets to be very, very problematic. So primary waves would cause these pushing together, which we remember called compressions, and stretching apart, which we call rarefactions, which some things might be able to take compression, but a lot of the building materials we use out there are not good for rarefaction or stretching apart. You think about like a bridge is not designed to just be, or a roadway I should say, is not designed to be pulled apart and then pushed together like right after one another. So you end up having these bucklings in the bridges, or I'm sorry, in a lot of infrastructure and in buildings too. Secondary waves would cause this up and down waving motion. It's not as problematic, but could certainly cause toppling of buildings. But the problem is when you put those two together. So imagine for a second that you have a pushing forward and backwards and an up and down at the same time that actually forms a circle. So these circular waves are called surface waves. And they really are the most damaging. There's a couple different types of surface waves because you can have one this way, you can have one this way. You can actually have kind of like all of them at the same time. And of course they have names. So these rolling waves, like I said, are called surface waves because they move on the surface. So just like in an ocean, it's kind of hard to picture how that could be a circle, right? But take a look at the red dot. Each of these dots maybe represents a molecule. It doesn't really. But the idea would be, it always feels like, if you were to just take a look at it besides the red dot, it just looks like water is moving and it keeps going in a wave. But that's not what happens in a wave in an ocean or in a wave in an earthquake. It actually goes up and down, but it also travels left to right at the same time. So most buildings are not going to be able to withstand that. A lot of places where they have heavy earthquakes on a regular basis, like say Japan or Mexico City, usually you have to design them to be very strong against these kinds of waves as well as basically primary or secondary waves. And if you're interested in why waves break, waves in a pool might go up and down, up and down. So why is it that waves crash and push out on a shoreline? That's a little bit of a deeper explanation, but if you want to, that video is there as well. So talking about these surface waves, when you have the surface waves that travel kind of like a circle, if you're looking down on the surface, that's called a love wave. I think it's named after a person. It's not like this is one you'll just love to have. And the Rayleigh wave would be a circular underneath the surface of the Earth itself, where it's getting pushed in and back and up at the same time. Both of those things just very devastating. Most of the natural disasters that have killed the most human beings in the last millennia have been earthquakes or tsunamis that have been caused by earthquakes. And even in most recent history, it's really hard to deal with Mother Nature with that much energy. Just another picture of these. So if you want to try these now, I know you still hopefully have your rope attached or your string attached to something. You could try to create these up and down motions, try and practice a couple of the primary waves, secondary waves, try and get both of them going at the same time for a surface wave. Just one more look at this, right? Just one more point to say, if you have some kind of a fault or some kind of a zone where you're going to have earthquakes happening, I'll remind you that primary waves, these rarefactions and compressions, will travel quicker than the secondary waves. But once they do get at the surface, even if this is traveling slower, a lot of times you have these aftershocks or these waves that keep coming and coming and coming, and eventually they're going to end up mixing at the surface, which is what causes those surface waves. Okay, that's the end of this lesson. Hopefully you've been able to practice a little bit and you have your diagram together. Don't forget to go do the exit ticket to get credit.